I'm here to I'm honored to present some of the findings that we had with our hypothesis about looking at the effects of math on college major choices. And this particular topic is quite interesting and affects all of us as academicians. I want to talk to you a little bit about what's been done in the past, and then talk about some of the data mining that we've done here in the United States, data for college students, and then talk about what that's revealed, and finally some conclusions that we've drawn from that regarding this new concept called mathematical curricular complexity. And so if you can keep that in mind as we go through. Here is a small snippet of data from just 5 different entities from the Integrated Post-Secondary Education Data System of the United States. This is public data, and you can see that we've about doubled the number of college students going over the last 50 years. And during that time, science and math has in the case of math, it hasn't grown that much. Chemistry's grown a little bit. That's my particular field. Engineering has grown proportionally to that, but health degrees have grown at 6 times the rate of anything else. So kind of an interesting caveat as we get into what is the crux of this situation. So U.S. college students apply to a college, they look at a prospective major, and then in the second year of college in the United States, they declare that major, and they choose a general area, normally humanities, arts, social sciences, business, or some kind of technical major. Or they can also choose a professional development major, which have become quite popular in terms of nursing and marine transportation, construction management, and we can talk about a lot of different ones that are there, but they lead to professional licensure, which has become very prominent in the United States. Students are inundated with a lot of different prospects from the internet, from broadcast media, from print media, and also their parents regarding many aspects of choosing a college, which is a monetary decision in the United States. And the focus has been the return on investment. And in the years where the college loan has become a major issue on the minds of students. So if we look at this historically in the last 20 years, the major research that's been done in this area has been done by economics professors, specifically econometrics professors. And their findings really had to do with, again, an economic base looking at this. What they looked at is an ability sorting in stratifying the majors. And the secondary and post-secondary grades, the human interactions that the students would have, they were questioning students as to the perceived work environments that they might be attracted to. And ultimately, the conclusions at the bottom of the page say that they're firmly centered on students maximizing monetary returns and even switching universities and if they were not offering what they wanted and to receive the return on investment. So these econometrics professors basically came to the conclusion that this was an economic decision. And so our hypothesis was completely different than that. What we wanted to know is, instead of querying over a dozen different variables and trying to weight them, what we did is we were looking at a predictive role of one particular aspect, and that is the cumulative achievement or mastery at increasingly challenging levels of mathematics. So the mastery at 4 critical stages is what we were looking at, the sort of pre-calculus level, calculus 1 and 2, calculus 3 and linear algebra, and then the transition to more theoretical advanced mathematics. And so these 4 demarcations is what we were looking at. And in contrast to that, we were also looking at the lack of cumulative mastery leading to the unwanted remedial time and effort that the student would have to put in. So we turned, instead of using some kind of subjective course difficulty rating system, we turned to a new concept created in 2018 by Heilemann called curricular analytics. And this was a method using math theory, graph theory that basically was used by the authors to try to um, outline a more constructive and better system of semester by semester schedules for students, but we're using it in an analytical sense. And so what we were looking for were some data. Um, we needed the majors in many different categories, and so we turned to our particular institution, which is a very highly competitive engineering or primarily engineering school. And that was very, very helpful in the fact that we were able to stratify the more fine detail of engineering. The the major contrast between our modeling and the econometrics modeling that was before us was that the broad categorization of humanities grouped with science and engineering, these were broad categories they used. We were much more fine in looking at it, as you'll see. So when we took the uh, suggested college schedule of just a wide variety of majors, we were able to start to map out, as I say here on the left-hand side, quantify the graph theory complexity by graphing this. And you'll see the graphical technique that I'm using in just a second. But I've outlined here the pure math that is required in this particular major called nuclear engineering at our particular school. Our particular school, as you can see at the bottom here, has its own nuclear reactor, which is really quite unique. But you can see the complexity that's already started to build up in terms of the arrows here. The arrows, of course, are one prerequisite leading to another, and or the sequential learning that one has to do semester to semester in some of the cases. And so, you have this, of course, in Spanish 1 to Spanish 2 and so forth, but certainly in the math and science fields, this is very prominent. And so this is a work to map all of these out. So the three aspects here, the first one is called a blocking factor in this graph theory method called curricular analytics. And the blocking factor is a quantification of the extent to which one course blocks the ability, if it is not passed, to take other courses within the curriculum. And so you can see that the numbers there within the circle are basically what the blocking factor is. And of course, there's a weighting by the number of credits that they are, but this is the quantity that we're looking at in this particular case. The second factor is called a delay factor, and this is the ability to successfully navigate relatively long course pathways without delay. And the delay factor is made up of the length of the longest path within the corresponding curriculum, which contains the particular course of interest. So you can see that the numbers have changed from the previous factor to this particular one. So what we're looking for is actually the addition or the summation of these, and you can see that I've added the blocking factor, the delay factor to come up with what we call the complexity. And so within the curriculum, we have a total complexity of all courses. And then what we're concerned about, or what our hypothesis involved, was the curricular mathematical complexity of just the pure mathematics courses. So here we have in the curricular analytics graph theory method, the edges or the arrows that are leading from one prerequisite to another. And you can see the requisite ancillary math classes that a nuclear engineering person is having to take, which are 6. And so I've outlined those in red for you. And you can see that on the right-hand side, the mathematical curricular complexity has a value here of 152, which isn't significant to you yet because you haven't seen it in context with all of the other majors. So I contrast here with 6 different math classes for a nuclear engineering major, and I take you to a physics major. A physics major is 7 different math classes as outlined here in red. However, you can see the mathematical complexity is only 127. And that is because you can see here in semesters 6, 7, and 8, a lack of connectivity in terms of prerequisite from the previous terms. In contrast to the previous one, which had a large amount of complexity to it. So the data on the US college graduates is organized by what we call classification of instruction programs. And so these are very specific. So that the challenge here was taking the 1,400 different majors that are classified under the US codes and trying to understand which ones are important, which ones to pick out. So here are 23 of them that we started out with in terms of mapping these originally. And you can see the number of total students. We did not mark for male versus female. We only took in terms of the total. And so in 2019 to 2020, here are our 42 different uh, uh, category majors that we have come up with the mathematical curricular complexity from the graph theory, along with the integrated post-secondary data system number of graduates. So if we plot this now, we had to differentiate again majors, chemistry versus biochemistry. We decided to do that. We grouped specialty areas such as astronomy, biophysics, and optics all under physics. So we had to look when to group things, when not to group things. And we took things like business management, economics, and econometrics, and of course, differentiated those because the mathematics were quite different in their requirements. So we used the flow charts, and then we looked at the statistical correlation between the mathematical curricular complexity and the number of U.S. degrees. So let me show you that graph. And this is a very messy graph. I just wanted to label it for you as to all 42 that are on there. And you can see that each of them has their own edge of the piece of these of the total information here. So let me clean this up for you a little bit and show you what the curve looks like. The curve is shown here in red dot numbers, the best fit nonlinear least squares regression. And you can see the fit on the top right is about 97.89. So it's really quite good. You can see the 4 different areas that we've talked about, the before calculus, the calculus 1 and 2, the calculus 3 and linear algebra, and then of course the more advanced math as you move into the majors such as nuclear engineering. But you can see the course progression on the top. These are the math progression that you come to in undergraduate mathematics. And so we tried to understand exactly where all of these 140 majors are leading to in our particular institution. So you can see here, this is the humanities, arts, and social sciences up here. You can see that there's not much math that is required, which you, of course, know already. But we looked historically, and you can see that this particular inverse relationship held over 50 years. And so this was not just a one-time occurrence. This is, again, over a half century of data. So again, this is very indicative that the dependency on cumulative math mastery is directly aimed towards the number of students finishing a technical major. And so the mathematical curricular complexity was observed to consistently produce a statistically significant coefficient of determination for the differentiable function over the entire academic breadth of the university landscape. And this was differentiated by taking a very fine differentiation under all majors in engineering, science, and mathematics. So the inverse relationship trend is a very unusual one. Usually we see logarithmic or other more mild correlations. This is a very, very, very strong trend. So the key to modeling here was, again, knowing or choosing when to group things and when to differentiate them. So some of the ramifications of this is the remedial mathematics causes a rapid increase in the delay And of course, the delay factor goes way up. And so, just as an example, with one delay, one course delay in a non-calculus one ready student in nuclear engineering, it would add 22% to the value of its curricular. Um, its curricular mathematics complexity. So it is a very, very strong function of remediation. So what we see in the attitudinal part of students is that oftentimes the delay and the pressure to pass remedial mathematics tends to discourage many students from seeking to go further in science and math. So in addition to increased time, the students also incur much more fees in terms of tuition, housing costs, and so forth. So the potential remediation underscores the true importance of backing up and looking at the cumulative mathematics mastery in higher education as it goes into both primary and secondary. So as we've seen in the US, the fall in mathematics scores over the last 50 years are having tremendous effects in trying to uh, also bolster this incoming student that wants to achieve in science, technology, engineering, and math fields. So again, these achievements are set, as I say here at the bottom, very early within a child's academic progression. So the suggestion is to look at that and being very important. I really thank you for your attention, and I'd be happy to take any questions.